So we talk about different bases, like, for example, if I had trichloroacetic acid, the conjugate base of that would be trichloroacetate. And if we compare trichloroacetate with just regular acetate, which one do you think is the stronger base? Acetate. Yeah. Then we look at this. These are what we call substituents. This is a methyl substituent. Actually, this is the methyl substituent. Methyl substituents are electron rich. You know, this is 2, 4, 6, 7, so this is -3. And so it's electron, we'll call electron pusher, whereas this one is going to be just 1. And so this will be +3. And this would be electron withdrawal group. And so if we withdraw electron density into the substituent group here, then that's going to make this less negative. Whereas this is electron pusher, and so it's going to make this more negative. And what we're looking for bases is how negative the donor atom is. You know, it should be pretty negative. All right. And so let's take a look at amines. Amines is a whole class of organic bases that contain nitrogen bonded to either hydrogens or carbons. Hydrogen and carbon has similar electronegativity, and so they don't have to. This is the amine substituent in organic chemistry. So there's a bond here, and you can attach this to different things. So we can attach an amine to this, you know, as well. That's different. There's the amine substituent, the amine ligand, and then the amine as a general class of organic compounds. These are organic bases. These are the amines here. And so ammonia would be an amine. But if we take one of the hydrogens off and replace it with a methyl group, then you know the electronic environment around nitrogen doesn't change that much. And so this is an amine also. And the base properties of these are going to be very similar. Now, if we take off if we take this off and put a bromine on there, then that changes everything. Because amines are going to be, well, we want electron rich on the nitrogen here. But if you throw a bromine on there, what's going to happen is it's going to suck the electron cloud density away from nitrogen, making it less basic. Okay? And so this is going to be more basic. In fact, the pKb, which is the power of the Kb, so this would be like 10 to the -4, 10 to the -5 as the Kb. 10 to the -4, but 10 to the -5, it's not that strong, considered weak. It's actually 1.8 times 10 to the -5. This one's 10 to the -3 to 10 to the -4. And so if it's 10 to the -3, 10 to the -4, the power, then you would think this would be a stronger base or a weaker base. In other words, this is about 10 to the -5. This is about 10 to the -3. Which one would be the Kb? Which one would be a more stronger base? Ammonia? Well, what is Kb? Yeah. Maybe I need to do that. The Kb equation is this. Okay, so we have ammonia plus water. Now, Kb is base plus water. This is going to yield ammonium and hydroxide. And so this is a pKb equal to 474, which is going to give us a Kb of 10 to the -4.74, which is 1.8 times 10 to the -5. Okay, if we go to methylamine, this would be CH3NH2. So we take one of the hydrogens off and replace it with the methyl group here. This is H2O liquid, and this is going to form methyl ammonium ion. So this is going to be CH3NH3 with positive charge and hydroxide. The pKb for this is 3.38, which is is going to give us a Kb equal to 10 to the minus 3.38, which is equal to what? And so, oftentimes, people express the Kb's in terms of pKb's, even though that requires an extra step. We have to do an extra step here to convert it into Kb, which is kind of a hassle. But the advantage of expressing things in terms of P power functions is it takes up less space. We don't have to write scientific notation. And that's nice for tables, because it makes the tables much more compact. And so I get 4.1. We're allowed two, remember, power functions, anything after the decimal is significant. There's two sig figs. So I'm going to get 4.1, and then I'll carry one extra digit. So this is going to be 4.2 rounded times 10 to the minus 4. So which one is a stronger base?
So you're asking which one hydrolyzes better?
Yes, which one's going to produce more hydroxide? The one that produces more hydroxide is going to be the stronger base. Does ammonia produce more hydroxide, or does methylamine produce more hydroxide? Methylamine. So methylamine is stronger base. Can you tell why? Well, even though hydrogen's electronated is 2.1, carbon is 2.5, but this carbon is more electron rich. Can you just look at it and see that's electron rich? I mean, what's the oxidation state on carbon here? -3. Oxidation state, well, actually, is it -3? Let's count. The oxidation state is going to be 2, 4, 6, and then it loses both of these. And so it's -2. Well, -2 is still electron rich. Right? What's the oxidation state on hydrogen here? +1. +1. And so, you know, even though this is going to be much more electron rich, but let's go on to here. You know, what's the oxidation state on this carbon here? This is ethylamine. This is a CH3CH2 from ethyl group. Ethyl refers to two carbons. Yeah, this is going to be -1, 2, 4, 5, -1. And this one will be well, actually 2, 4, 6, 7, because it splits this. So -3. So this is -1, -3. Do you see this is an electron pushing group here? And so it's going to make this nitrogen a little more negative, which means it's going to be a little bit more basic. But it's not tremendously so, because it's 338 versus 337. This one's slightly more basic than methyl. So ethylamine's a little bit more basic.
So by quick glance, we can take the power of Kb, pKb. The lower the number is, the more basic it is.
Right. Because it's the invert. It's kind of inverse relationship, because it's the negative power. If it weren't the negative power, then it would be the opposite. You know, it's the negative. And so for all power functioning, it goes the same. The smaller the power function is, the more stronger it is. It goes for like pH. You know, when we're looking at hydrogen ion concentration, the smaller that pH is, the more hydrogen ion we have. And then we have things like this. This would be an acid here. Now it's a benzene ring. Do you guys remember the benzene ring? What do you remember about the benzene ring?
Ring of carbon attached to hydrogen.
Yeah, carbon attached to hydrogen. What do you remember about the pi bonds in the benzene ring? Do you guys remember the what we call this? You know, when we look at the pi bonds, so for example, let's say we had alternating double bonds here. So let's make a double bond here, and here, and here. And then we'd have one resonance form. for this, right? And so we have these PP pi bonds here, and then the other resonance forms. So the hybrid is actually going to delocalize. When we have this alternating single double bond, it's called a conjugated system here. And so this is conjugated. And so when we have this conjugated alternating single double like this, then what we have is total delocalization over that. And so the bonds are special in benzene. If you recall, the bonds are a bit stronger than what was be predicted based on just having a bond order of 1.5. And so there's a whole thing in the bonding chapter on benzene, which is pretty important because benzene.
So they're not order one?
They're a little bit stronger than bond order 1.5 would predict, like a typical 1.5 because of this conjugated. This is called an aromatic. Aromatic compounds have this alternating double single. Actually, we can see that back. What chapter was that? Chapter 11? It's called delocalized electrons. And the whole section on benzene, bonding in benzene, and the whole history of this. Here. So the pi bonding network, and then MO theory. MO theory is much better at explaining this than valence bond, but essentially the electrons are completely delocalized. This is MO. This would be valence bond here. And so we see this, in other conjugated things like this, ozone. We get this delocalized. And so what that means is this, if we have a benzene ring, you think of benzene as being electron rich, but actually the benzene ring, interestingly enough, it's a hydrocarbon group, so it's carbon and hydrogen. Hydrocarbons are very flammable, and benzene burns very nicely. Benzene was banned for a long time because benzene was a carcinogen. But
so we're going to get on that?
Because you just have to take special precautions in handling it. And so the people who banned it weren't people who were actually using this stuff. As long as you take special precautions, they're okay working. I mean, benzene's in gasoline, and they can't ban gasoline yet, but we'll see. But there's history. Benzene is a very useful solvent. I don't know the whole story because that was before I started working in chemistry, and then it was brought back. And if they're using it in rubber cements and paint remover, maybe it shouldn't be in those consumer products, but they banned it for chemistry labs too. So yeah, I could understand why they ban it for consumer products. But people in the lab weren't allowed to use it, and so that was the difference. Here it is. The U.S. banned benzene's use nearly 45 years ago. In personal care products, though, I understand that. So yeah, it should be banned there. But in a chemistry lab, it probably shouldn't be banned in a chemistry lab because chemists are trained to handle this kind of stuff. Chemists have hoods, that they can use, so they don't have to inhale benzene vapors, et cetera, et cetera. So benzene is a special substituent. Normally when we think of hydrocarbons, we think of electron rich, All hydrocarbons are electron rich. All hydrocarbons are very flammable. All hydrocarbons are good reducing agents. Yeah. But benzene, it's because of this delocalized cloud, the pi bonding, alternating pi bonding network, benzene's not treated as an electron pusher like you'd think. Benzene should be an electron pusher. Hydrocarbon groups should be electron pushers. Let's take a look at what they say about benzene here. So, an additional electron withdrawing effect is seen in amines that are based on the benzene ring. So if we have a benzene ring, electron withdrawing benzene, that's kind of odd, or related structures. These are aromatic amines such as aniline, So normally if we have an aniline, which is a benzene ring attached to NH2, we think, okay, that's going to be electron pusher, and it's going to make aniline more basic. But it turns out that it's based on benzene, which we learned in section 11.7, so this is back in Chem 1A, and depicted in several different ways. We figure it's 1129, 1130, 1131 is a 6-carbon ring with unsaturated, et cetera, et cetera. Cyclones, the studies with this unsaturation are said to be delocalized. Okay, so as suggested by the following structures, to some extent, even lone pair electrons in the amine group participate in the spreading out of delocalized electrons. The curved arrow suggests progressive movement of electrons around the ring. And so what these are resonance forms that show that the electron cloud can be delocalized within the ring. And so we normally do this for Lewis acids and bases. We draw these little arrows showing how we can rearrange the electrons here. This is called a mechanism. A mechanism just shows you how mechanistically, what we can do with the electrons here. And so there are different ways of imagining this benzene. This benzene group, if we attach, let's say, an amine to this, here. Is this benzene group going to make that nitrogen more negative or less negative? Well, we typically think it's going to make it more negative because if we look at benzene here, let's look at part of benzene here. Actually, we'll just draw the whole thing. This is pretty easy to draw. All these are sp2 and valence bond, and these are LsP2 trigonal planar. This is flat, pancake-like structure. What's the oxidation state of this carbon? Okay, so we have 1, 2, 3, 3. This carbon would be a plus 1. Oh, that's oxidation state. That's not formal charge. I usually circle oxidation states. Don't. The oxidation state of this carbon? -1? Yeah. 1, 2, 3, 4, 5. -1. This one would be the same, -1. This one, same. Is it?
Yeah.
1, 2, 3, 4, 5. Yeah. 1, 2, 3, 4, 5. And the hydrogens would be false 1. So overall, I would think the benzene would be, even though this is a +1, so it could be electron withdrawing. Overall, I think that it's kind of electron rich, right? Benzene ring burns. That's why it's in gases. This kind of stuff. Although I'm not sure how much benzene is in gasoline. There are substituted benzenes, where they put the different groups on that. Gasoline. Okay, going back to this, there are different ways of kind of visualizing this. One way you might have said, well, this hydrocarbon is going to be electron pusher, except for this carbon, which might be electron withdrawer here. But then we can explain it in other ways. We can delocalize the electron cloud density into the ring. And the way we could do that is this. If we take this lone pair and drop it into the bond here, that's going to form a double bond. Okay, so we drop the lone pair here, but if we form a double bond to this carbon, there's too many bonds. We can't have 5 bonds with carbon because it's an octet law for carbon, nitrogen, oxygen. They can't exceed an octet. And so it's going to kick these out, and it's going to form a carbon anion here. And this carbon anion is going to have, the organic chemists, they don't like to write hydrogens here because they like to do things in shorthand. And so if we do this, this is what it's going to look like here. We drop the lone pair into the bond here and kick out these and form an anion like this. And so we're going to get this structure that results. The structure that results is going to have a carbon nitrogen double bond. There's no more lone pair here, so nitrogen does not exceed an octet. And then we're going to make this a single bond rather than a double bond and throw out the lone pair here. There's still a hydrogen attached to that carbon there. And so the rest of this is going to look the same. Like that. Okay, now that's going to change the formal charges. Now, oxidation state and formal charges are 2 different things. What are the formal charges? What's the formal charge on nitrogen? Oxidation state didn't change. The oxidation state is still the same, but the formal charge did change. What's the formal charge now? Yeah. How do we count a formal charge? Sharing electrons. So 1, 2, 3, 4. How many is it supposed to have? 5 plus. This carbon is still the same. 1, 2, 3, 4. This carbon, however, is different. 1, 2, 3, 4, 5. What's the formal charge in this carbon? Minus. Okay. So this structure obviously isn't as good as that structure. But this is a little bit higher energy, but what it shows is that the electron can be kind of pushed into the ring, electron density, making the nitrogen more positive. There. Hybridization did change. What's the hybridization on this nitrogen? If you're taking organic chemistry, you need to be able to instantly tell me what the hybridization of this nitrogen is, but just by looking at it. If you can't, then you need to review that before taking organic chemistry. Otherwise, you're going to... organic chemistry is already hard enough as it is. You don't want to make it harder by trying to review all this Chem stuff. No. It's SP3. SP3, 4 groups. This is going to be tetrahedral. Trigonal pyramidal is the molecular geometry. Tetrahedral is electron geometry. Tetrahedral electron geometry requires SP3 orbitals. And so this is SP3 hybridized. Then it switches to this hybridization. What's this hybridization? Not trigonal pyramidal. Well, hybridization is SP something. Trigonal pyramidal will be the molecular geometry of this. This is trigonal planar, is the molecular geometry. Trigonal planar would require what hybridization? sp2. So this is sp2. So we went from sp3 to sp2 there. And then this carbon used to be sp2, but according to this, it should be sp3. But you know, the weird thing is that the hybridization could be impacted depending on how we can delocalize the electron cloud. So if we keep this sp2 hybridized, then there are going to be greater repulsions. However, if we keep this sp2 hybridized, there's going to be unhybridized p here that can delocalize in the ring. And so this one retains its sp2, even though you predict it should be sp3 based on Chem 1A. But it retains its sp2 so we don't break the aromatic part of the ring, which is the delocalizing the electron cloud over the entire structure. And so in that case, then, what we predicted, the sp3 is going to have greater repulsions, but then it could have fewer repulsions because we can delocalize electron cloud in there. Does that make sense? So there's actually a homework problem in Chem 1A that in the advanced section that it's exactly kind of like this. But it just is one of those kind of things that, you know, something else takes precedence. And so what you predict based on Chem 1A is not what's necessarily observed. It's all right. There. So next, we can generate more resonance forms for this. These are all resonance forms, and they are, you know, this is higher energy than the original structure because of the formal charges that we generate. But then what we can do is we can drop the lone pair here and create a double bond here, and then kick these double bonding electrons out there. So we can move the charge. The negative formal charge is on this carbon, now it's on this carbon. Then we can drop it down here and move it out here, now it's on this carbon. So the negative formal charge, well, in reality, all structures will contribute to the resonance hybrid. So what we're going to get is we're going to get a negative charge on these two carbons and this carbon here. We give names to the carbons in the ring here. These are called orthocarbons. Orthocarbons are adjacent to the substituent, so the orthocarbons are going to get negative. These next two carbons here are metacarbons, and this final carbon out here is a paracarbon. And so the orthocarbons and the paracarbon are getting the negative charge here. So that makes a difference. Where we put certain things will make a difference. So if we put an electron pusher group on ortho and para positions, electron pusher, well, that's going to make these even more negative, and it's less likely to delocalize a charge, and should make it maybe more basic. However, if we put electron withdrawal groups here, well, actually, let's talk about it with a specific example. So here is an example of this. This is a hydrocarbon group. This is cyclohexane. There are two hydrogens on each of these. These are sp3 carbons. This is aniline, which is sp2, or phenylamine. Sometimes the benzene group is called phenyl group. And if we look at aniline, versus both of these are hydrocarbon groups, right? But look at the difference in basicity. If you look at cyclohexylamine versus aniline, which one's more basic? By how many orders of magnitude? 6 orders of magnitude more basic. A million times more basic. Why? Because a cyclohexyl group, which is this, is an electron pusher. You know, cyclohexyl, if we look at cyclohexyl group like that, this is going to be sp3 carbon. So we can just take a quick look and look at the okay, tell me the oxidation state on this carbon here. All the formal charges are 0. What's the oxidation state on this carbon?
0.
So this is 2, 3, 4. So this is 0. This carbon?
Minus 2.
Minus 2? That's good. So that's 2, 4, 5, 6 minus 2. This one? Same. 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 So do you see this group is a lot more electron rich? This is going to be electron pusher. The electron pusher is going to make this nitrogen more negative, which is going to make it more basic. And the bases we want negative, acids we want positive. And so in this case, the KB is between 10 to the minus 3 and 10 to the minus 4. When you look at aniline, aniline is not very basic at all. This is has a KB around 10 to the minus 9. KB around 10 to the minus 9 means that this must be an electron withdrawer. You see it's sucking electron density away from nitrogen, making it less basic. Quite a bit less basic, and that's we can visualize in different ways. One, we can visualize as this aromatic delocalization can accommodate more electron density, spread it out. Two, we can come up with resonance forms that show delocalization of electron cloud density into the structure. The more resonance forms you can draw, the more delocalization of the cloud. Okay, now we have 2 chloroaniline here. What's having a chloro group going to do to this? What's having a chloro group going to do? Well, the chloro is electron withdrawing group or electron pusher group? A chloro, well, what's electronegativity of chlorine? It's pretty high. I mean, it's right next to fluorine. Fluorine is the highest. Fluorine is going to be the most electron withdrawer group. And in fact, chlorine has what we call the highest electron. What is that? Electron, what is that called? Chlorine has the highest electron affinity, right? Do you recall electron affinity? Electron affinity is the ability to attract and hold on to electrons here. Chlorine's at the top there. And so chlorine's electron withdrawal. And so if we put a chlorine on the para position versus a chlorine on the ortho position, it makes a difference. Do you see that? When we're looking at this, well, why would it make such a big difference here? If we go back here, we're putting an electron withdrawing group here. This is just observational. Did I do that? Here. So we'll put a chlorine on the ortho position and the para position. And it appears to make a difference here, whether it's on the ortho or the para, but when we look at it, the negative charge can be on the ortho positions and the para positions. So number one, putting electron withdrawal is going to make it even less basic. Do you see that? So we go from a pKb of 9 to a pKb of 10. It's less basic because not only do we have delocalization into the ring, we have what's called the inductive effect, right? The inductive effect is sucking electron cloud density towards the chlorine, the more electronegative atom here, making this even less basic. Now,
it would seem that if pulling everything like towards just this is the left side, wouldn't that make the amine group more basic?
No, we want to push all the electrons onto nitrogen. That makes it more basic. By sucking the electron out, we make it less basic. Yeah, it makes it less negative. The more negative charge we have, the more delta minus we have in nitrogen, the more basic. Think about water versus hydroxide. Which one is a better base?
Hydroxide.
Yeah, hydroxide has a full negative charge on there. It's a negative formal charge. And water has a partial negative charge, which we call delta minus. And hydroxide is much better base than water. Orders of magnitude better base. And so we want to concentrate the negative charge. And so this, well, it seems here that the chloro is even more effective at withdrawing electron cloud density than the para. This could be due to a couple of things. One is the distance. You know, the ortho positions are adjacent here. The para is more atoms removed. Or, you know, these are things we hypothesize. This is the data, and so we try to hypothesize. Now for meta, here, the pKb for meta is 1066, which puts it somewhere between here. And we look at the negative charge in the delocalized ring. It's not on the meta position here. It goes ortho, meta, para. And so what do they say? Let's see what they say about this. Replacement of a ring-bound hydrogen atom in aniline with an atom or a group that has high electronegativity, well, chlorine has high electronegativity, causes even more electron density to be drawn away from the mean group, further reducing the base strength. Also, the closer this ring substituent is to the mean group, the greater is the effect. And so I guess it is a distance effect here. You know, the closer the distance, the more effect it, or the more impact it has. And in organic chemistry, we have names for the carbons. So this would be the alpha carbon, this would be the beta carbon, and then the gamma carbon, and then the delta carbon. And we look at the substituents on the alpha carbon, the beta carbon, and see, you know, and the impact there, you know, as far as the distance goes from that. Alpha, beta, ortho, meta, para, you don't need to know, you know, what ortho, I'm just talking about it because they talk about it here. Okay, now, are these acids or bases here?
Bases.
Well, these could go either way, but, you know, when we look at this here, it's a pKa, so we're talking about acid, and we're talking about how acidic this is. So this looks like an alcohol. In fact, this is an alcohol. We call it phenol. This is phenol, which is a benzene ring, alcohol, and phenol for short. Are alcohols very acidic? No, alcohols are not very acidic. And the pKa's for alcohols are huge, like more like 20, you know, like 1 billion times, 10 billion times weaker than this. But phenol is unusually acidic. Do you know why phenol is unusually acidic? Normally alcohols are not, but this pKa of 10 is unusually acidic for an alcohol because alcohols don't have pKa's this low. And this isn't a very strong acid, of course. And so one thing is because in most alcohols, you know, it's a COH, and the C is an electron pusher. However, this C is going to be an electron withdrawer because of the benzene ring. And so that makes phenol orders and orders and orders of magnitude stronger in terms of acid properties than a typical alcohol, like ethyl alcohol. Ethyl alcohol is not acidic at all because you have the ethyl group. The ethyl group is an electron pusher. But now if you have a benzene group here, it's an electron withdrawer. And it's going to make this more. What about chlorophenol? Should that be even more acidic or less acidic?
More acidic.
It should be more acidic. Why should it be more acidic? Because it's going to withdraw even more and make this hydrogen more positive. For acids, we want positive charge. For bases, we want negative charge. People confuse that all the time. And then another thing that people think is they always think in terms of electronegativity. Don't think in terms of electronegativity, you know, because somebody wants a simple rule. The more electronegative, the more acidic. But that doesn't always work. And so what we look for is what's happening, you know, what's happening to the hydrogen here. So people get this mixed up all the time. Like, for example, here. Oh, gosh. So people think in terms of electronegativity, well, it's discussed here, but in this case, this is more electron withdrawing than this is the chlorine versus bromine. So in this case, it works. But when we're thinking about bases, so hypochlorite versus hypobromite ion, which one's more basic? And so if we're thinking about bases, then you have to think in the opposite sense. And so what would be more basic, hypochlorite or hypobromite?
Hypobromite.
Yeah. And so hypobromite is more basic. Well, it's more basic, is that because bromine's more electronegative? No, so we can't use well, we could use it in this case because we could say hypochlorite is less basic because chlorine's more electronegative. And so that argument would work. Okay, so what did we predict for this one? It's going to have a lower pKa or a higher pKa? Lower pKa. Lower pKa is more acidic, and we're a stronger acid. So we would predict this one would be a stronger acid, right, because of the inductive effect, we can say. There's another thing that impacts acid strength, and the other thing is the stability of the conjugate base, and that's talked about here. The stability of the conjugate base. And so when we look at acid strength depends on the HX bond or the HA bond. The weaker the bond, the better. It depends on the polarity. The higher the polarity, the better, but there's, there could be conflicting results from that. And it depends on the stability of the products. And so this is talking about the stability of the products here. Stability in the sense of aqueous solutions. And so they're talking about increasing stability this way and that way, but I'm going to skip this for now, unless we look at a specific example. Okay, let's look at Lewis acids and bases next. Lewis acids and bases are a bit more complex, and we do this mechanistically. So let me just give you a quick overview of what they're doing here. With Lewis acids and bases, we do these mechanistically. And so Lewis base is electron pair donor. So we have an electron pair here, it's being donated to boron. So this will be a Lewis acid base. Here's our Lewis base. This would be our Lewis acid, BF3. BF3, one thing about BF3 is it's lacking an octet. Fluorine refuses to form double bonds because if fluorine double bonds, it put a positive formal charge on fluorine and a negative formal charge on boron, which isn't going to happen. So fluorine's not going to release the lone pairs to boron, and so we're going to have less than an octet, which makes BF3 a powerful Lewis acid. And so we'll take ammonia and then we form this, a bond. This is a coordinate covalent bond. Well, we've seen coordinate covalent bonds before. Where have we seen those? Or dative bonds, coordinate covalent or dative bonds. And coordination compounds, exactly. Those are all. And so this forms this. Let's call it a Lewis acid base adduct or the product. And so the product is we just form that. Here's another Lewis acid base reaction. Oxide and calcium oxide. This would be solid. And we're reacting with SO2. So we'll take a lone pair off here and bond it to the sulfur. We'll form calcium sulfite. This. Here we have the coordination. Okay, I think actually this is a little bit different. This is called hexa-aqua aluminum 3 ion. Hexa-aqua aluminum 3, did you know this stuff is more acidic than acetic acid? And that's because the inductive effect. Aluminum is what charge here? Plus 3. Plus 3 makes this heavily electron withdrawing, which is going to suck water away from the aqua groups. Not water. What does it suck from the aqua group? Electron cloud density. So it sucks electron cloud density away from this, making these hydrogens even more positive. And so that's what makes this complex so acidic. The pKa for this one's, or the Ka for this one's like 10 to the minus 5 or so. Is it on the chart there? Yeah, it is. You see, I actually it's just slightly less acidic than acetic acid. So here's the hexa-aqua, 10 minus 5. So it's fairly acidic. Acetic acid is 1.8 times 10 minus 5, so a little bit more. And so that's it. And this is actually a polyprotic acid because they're more water aqua groups. But once the first one's taken off, we form a hydroxyl group or hydroxide group. And so this water is going to pluck off that proton to make hydronium. And then these lone pair are going to go here to make hydroxide. And so we have a hydroxo now complex, as well as the 5 aquas here. And so this is the Ka reaction. The Ka reaction is just shown here. The hexa-aqua aluminum 3 plus water forms hydronium plus this. How would we name this? We would name this penta-aqua hydroxo aluminum 3. Yeah, okay. Okay. You may be wondering why sodium ion does not act as an acid. It has to do with charge density. Sodium is kind of a big ion with a low charge. So it's not going to be very acidic, not like aluminum. Aluminum ion is tiny with a high charge, making it much more acidic. So this is positive. This goes for the group 1. The group 1s are all neutral in solution. So we can see it here based on charge density. When we look at the group 1s don't have very high charge density, and they aren't very acidic in Lewis acid-base reactions. Let's compare that to aluminum. Aluminum's very acidic, in solution. It's got the pKa of 5, so it's quite a bit acidic here. And so these we consider neutral, pretty much. Beryllium's tiny, and so it's fairly acidic, but things like calcium, calcium is not very acidic, 12.8, Magnesium is not very acidic, 11.4. And so what we're looking for are small, tiny ions like beryllium. It's pretty acidic. Look at this, titanium, iron 3. Iron 3 is very tiny, pKa 2.2. We can draw a chart like this, and we can see a rough correlation. If we look at the pKa is roughly correlated with the charge density. So this is just one of these observational things. And so especially at high charge densities, as we get to low charge densities, the correlation doesn't look very good, for that, even though this one doesn't have that very high charge density, but it's very acidic, So there must be other factors in addition to this. And so charge densities is one of those things we look at. It's not a perfect correlation there, but it's okay. And so these are the metal. And so these are all Lewis acids. Some of them are very weak, like sodium. Some of them are quite strong, like iron 3. And so this is one of the things we can use, but it's not perfect, like we said. Up here it's pretty good. The weak ones, but down here it's not. There's other factors because there's some covalent interaction in the bonds here. If this are strictly ionic, then it should be pretty well correlated. Okay, so we're going to look at some other Lewis acid base. Let's take a look at analyzing things based on Lewis acid base properties here. Maybe we'll do this one. We'll do lime and water. I'm going to draw out the Lewis structure. When we do Lewis acid-base reactions, we draw out the Lewis structure. Lewis structure for our ionic solid would just be a lattice of ions. Etc. And just go up. Let's say this is the surface of the crystal here. All right, so what we see is Lewis base. Right? Which one's a Lewis base here? Oxide or calcium 2+? Calcium 2+ would be the Lewis acid or the Lewis base? Yeah, this would be a Lewis acid here. This would be an acid. It can, no, electron pair. Is calcium very good Lewis acid? Well, let's take a look here from the data. Is calcium a very good Lewis acid? No, in fact, it's incredibly weak. 10 to the minus 13. What's water? Water's Kb is 10, Ka is 10 to the minus 14. You know, it's pretty weak. So it's not very good. How about this? This oxide would be the base. And is oxide a good base? Well, is oxide a good Bronsted base? So go over to the chart here, and what's the number 2 base? Number 2 most powerful base on this chart. Oxide. Oxide, in fact, oxide's too powerful to exist in water. The strongest base that can exist in water is hydroxide. So oxide doesn't exist in water because you can't make an aqueous. Let's say you tried to make a 1 molar aqueous solution of oxide, you wouldn't be able to. Because what's going to happen is the oxide is going to immediately attack water to form hydroxide. So oxide's a good Bronsted base, but it's also a good Lewis base, you know. And so we'll look at water next here. So oxide, this is the base. Water is both an acid and a base. The acid would be what? The hydrogens. The base would be the oxygen. And the hydrogens are delta plus, making them willing to accept electron cloud density. The oxygen is delta minus, making them, able to donate electron density. So this is what we're going to have here. We're going to have this. We're going to have the oxygen. Let's say there's a collision here, and this, do you know what orbital this is? What hybridization is oxide? Okay. Well, there's other ways, like, I think when I was learning hybridization, I do SPPP. Each pair of electrons requires an orbital. And so SPPP is SP, SP3. But that doesn't always work, because if it's SP2, then you know, it's just, it's not really theoretically based. It's just one of those things that helps you do it. And so if we had a double bond and two single bonds, that would be spp. You know, even though I just said each pair are. So there are different things you can do to try to remember. But anyway, the base attacks the acid. And so this sp3 gets pushed into the S. Valence bond theory is very useful for this. What kind of bond is this? This is what we call an s-sp3 sigma bond. And so as this sp3 gets pushed into the s orbital there, it kicks out these electrons into the sp3 orbital on oxygen. And so we break that bond. And so what we're going to form is we're going to form an sp3 s sigma bond here. And then what's going to happen is, well, we can't have too many bonds to that. This is going to break off. In other words, the s-sp3 overlap is going to break, and then the electrons are going to go into the sp3 of oxygen there. And so we end up with this. Okay. And so this was the sp3 that was overlapping with that hydrogen, but it got kicked out. Does that make sense? And so what we do is this. You learned this in Chem 1A. Metal oxides and water. Metal oxides and water form metal. Well, actually, it's not metal oxide. Metal oxides and water. Maybe you learned this in Chem 1A. Yeah. Yeah, will form metal hydroxides. Actually, that's not, I don't like that necessarily. Calcium hydroxide. Hydroxides are all soluble, or no, calcium hydroxides are all insoluble, right? Except for which ones? Except for calcium, strontium, barium, group 1, ammonium, right? And so this is going to be aqueous. So this should dissolve. This is what you might have learned in Chem 1A. You might have learned that metal oxides are basic. Calcium oxide is metal oxide, it's basic. You might have learned that non-metal oxides are acidic, and that semi-metal or metalloid oxides, we'll just call it semi-metal oxides, are what we call amphoteric. So back in this chapter, like aluminum oxide can act either as an acid or base because it's right on that metal. The aluminum oxide is kind of interesting. But calcium oxide is clearly the metal side, so that's clearly a base. But carbon dioxide would be clearly the non-metal side. It's not semi-metal, so that should be acidic. And so let's look at carbon dioxide now. And so this would be kind of the Kb kind of equation for calcium oxide solid. So base plus water. Okay, let's look kind of at the next example here, CO2, which is a non-metal oxide. So, but you know, CO2 has both acid and base sites. We call individual atoms that are either acidic or basic sites. And so what is the acid site? What's the base site? Well, in CO2 can act as a base. And so oxygen here would be a base site because it's got a delta minus, right? And it's got lone pairs. The charge is important. It's not just having a lone pair. For example, here, nitrogen trifluoride has a lot of lone pairs. So you look at nitrogen trifluoride and you might say, okay, that's a base, the nitrogen, and the fluorines are base. But do fluorines want to donate a lone pair to anybody? No. If they did, they double bond. They never double bond. What about this nitrogen? Is this an amine? You know, amines are basic. Would you suspect this nitrogen would be very basic? Well, one thing is no, because the nitrogen is going to have a positive charge, not a negative charge. And another thing is, what is the oxidation state on that nitrogen? +3. If you look at any amine, let's go to trimethylamine. If we look at trimethylamine, what's the oxidation state on the nitrogen? Well, for one thing, nitrogen has a delta minus, making it basic. You know, nitrogen is more electronegative than carbon. And what's the oxidation state on nitrogen there? -3. And so you can see there's going to be a dramatic difference between these two. And therefore, this second one is not an amine. This is not an amine. Whereas this is an amine. And so over here, you know, yes, we learned in Chem that non-metal oxides are acidic, but they can also be base as well. This is non-metal oxide, it has a base site, 2 of them. And so we're going to get away from these general statements like this in Lewis acid base and look at the structure and then determine what's acidic and what's basic. And so I don't talk about this much at all in Chem, but I did see it on the standard test. And so we have 2 base sites. Okay, is there an acid site? Yes and no, there's an acid site. Carbon's going to be delta plus, making that an acid site. But there's one problem with carbon accepting a lone pair. What is that one problem? If carbon forms another bond, what's going to happen? It's going to have 5 bonds. Is carbon allowed to have 5 bonds? Carbon's not allowed to have 5 bonds, because that's a law for carbon and other secondary elements. If it were, let's say, silicon, yeah, maybe silicon can, or germanium, but not carbon. But what we can do is this: we can rearrange the electrons. If a bond forms here, we've got to kick out the pi bond. And so this turns out to be an acid site here. Yeah. Okay, we already looked at water. You know, water has both acid and base sites. And so we're going to do this, Lewis. We have different choices. So let's say the base site on CO2 attacks the acid site on water. And so if the base site on CO2 attacks the acid site on water, it's going to kick these electrons out, like that. And what will we form? What we're going to form is this. What's the formal charge on this oxygen? Yeah, +1. This doesn't look so stable because of the formal charge. And then we can try to stabilize that. You know, we can try to stabilize that by taking this double bond and giving it to the oxygen. If we take this double bond and make 2 lone pairs on the oxygen, that would be great. But the problem is this. that would leave the carbon with less than an octet. Well, that's okay because we could fix that by putting a lone pair into the bond like this. And so one way we could take this is like this. We'll break up that pi bond and make it a lone pair. And then to satisfy carbon's octet, we'll drop the lone pair in there. And so we end up with something that looks like this. We end up with okay, so now the formal charge on this oxygen is now 0. However, the formal charge on this oxygen is now plus. You see? And so we end up kind of with a dead end. We don't really make anything more stable. Okay, or we can try this. What if the base site on water attacks the acid site on CO2? And so, or the base site on water attacks the acid site on CO2. Then I have 5 bonds. I can't have 5 bonds. But if I kick out one of these pipes, then I can drop that down to 4 bonds. And so what does that form? Okay, that's going to result in a structure that's going to look like this. What are the formal charges here? These are reversible, by the way. Okay, this oxygen up here has a formal charge of plus. If we have an oxygen with a plus, you know what that does? It makes the hydrogens a lot more acidic. You know, think about hydronium. Why is hydronium so much more acidic than water? It's just got OH bonds, just like water. So what makes hydronium so much more acidic than water? Basically the inductive effect, because what's the formal charge on the oxygen here? Plus. This is the same reason why aluminum, the aqua complex aluminum are so acidic, even though it's just water. And so what we have here now is we have electron withdrawing occurring into the oxygen because of the positive formal charge, making these much more acidic. So this is, when I look at these hydrogens, I think, wow, those are pretty acidic hydrogens, right? What makes hydroxide a good base? Hydroxide is an excellent base compared to water. Hydroxide is a much better base. Why? Because it has a full negative charge rather than a partial negative charge, like water. Water just has a partial negative charge. And so hydroxide is an excellent base. And so when I look at this, I see a pretty strong acid, Bronsted acid. And when I look at this, what's the formal charge on this? Minus. I see a strong base. Do you see that too? We've got a strong acid and a strong base in the same molecule. Now, you know, what types of motion are there? What types of motion do we have in chemistry? We have vibrational motion, rotational motion, and translational motion. So what's happening here are these are vibrating.
And what if this vibrates like this? What if this strong base sees this strong acid and they contact one another? What do you think is going to happen when the strong base and the strong acid come into contact with another? We're going to have an acid-base reaction, right? And so this is what's going to happen here. The strong base, this vibrations, and so this sp3 gets pushed into the S and then kicks these out. And so this is what we call an intra means within. This is what we call an intramolecular proton transfer, and it's just an acid-base reaction that occurs within the molecule. And so intramolecular proton transfer. Normally when we have an acid-base reaction, it's between two separate species, but this is an acid-base reaction that occurs just within the same. So if we have that occurring here, then what results is this. Do you recognize this molecule?
Acetic acid?
No, not acetic acid. It's H2CO3. What's H2CO3 called? Carbonic acid. Carbonic acid is inherently unstable and decomposes into CO2 and water, but this is an equilibrium. And so what happens is a tiny bit of carbonic acid does form when CO2 is dissolved in water. And so if you take a straw, if you take a straw and blow it into an acid solution with phenolphthalein, eventually it'll turn pink as you're exhaling CO2 into it. And so this is what makes our DI water so acidic. Our DI water is stored in a tank in the attic space. And the tank has air in contact with it. The air has CO2. The CO2 gets dissolved in the water, Henry's law, and makes the water acidic. And so the pH of our DI water should be 7, but the pH is closer to 5 because of the CO2 and the carbonic acid that's dissolved in that. And so this is the equilibrium between CO2 and water and carbonic acid. And it's heavily favored to the left. And so K for this reaction is very small, but still it's big enough to create, hydronium. Water will get the hydrolysis. All right, that's this is chapter 16. Basically, we're going to move on to chapter 17, but how much time do we have? 10 minutes. Okay, let's take a look at chapter 17. Here. Chapter 17 is just a continuation of acid and bases. And so this is acid-base part 2. Additional aspects of acid-base equilibrium. Here we're going to look at more complicated mixtures in chapter 17. Here we got the titration, phenolphthalein indicator. So we'll be looking at titrations, but basically, when we look at the sections here, 17.1, common ion effect. We've already been talking about common ion effect. 17.1, we're going to be looking at different mixtures. 17.2, we look at one specific type of mixture. In 17.2, we're going to look at a mixture of a weak acid and a weak base. Those are called buffers. In 17.3, indicators. 17.4, titration. 17.5, salts, polyprotic acids. 17.6, acid-base equilibrium calculation. Just more acid-base. I think in a nutshell, 17 is acid-base mixtures. Acid-base mixtures. Here we can see, in our study of acid rain, I didn't talk about that. We learned that a very small amount of atmospheric CO2 dissolves in rainwater. Yet this amount is sufficient to lower the pH of rainwater by nearly 2 units. So we go, rainwater is pH 5. It depends on where the rain is. You know, where there's a lot of coal, you know, with high sulfur content, the pH is even lower. Some of the lowest pHs for rainwater are like in the pH 3, pH 2 range. In fact, some lakes actually have very low pH. There's some lakes in the old industrial areas that have pHs that are highly acidic. In fact, there's one in Canada. I was just watching this YouTube video where they have somebody there during the day because to shoot guns at migrating birds. Did you see that?
Yeah, I've seen that.
Yeah, so they don't shoot the birds. They just
shoot near them so they fly away out of
Right.
the water because it will literally eat them.
right because the water will eventually kill them. So they try to keep the birds out of there. Oh, it's pretty interesting. But you know that the pH of that lake was like pH 2. Can you believe it or something like that? That's crazy. pH 2. Well, anyway, but you know things like sulfur dioxide, sulfur trioxide from coal, and nitrogen dioxide from automobile and diesel will also create very acidic waters. Remember, so CO2 and water, Lewis acid base. SO2 in water, you know what SO2 in water forms? CO2 in water forms carbonic acid. Can you guess what SO2 in water forms? Sulfurous acid. Yeah, and SO3 forms sulfuric acid, and NO2 forms nitric acid. Those are all Lewis acid base reactions, which we do mechanistically. This is called the mechanism in organic chemistry. In organic chemistry, you do a lot of this stuff because the reactions are kind of complicated, and all the reactions are electrical in nature. So we look for, you know, areas of negative and areas of positive charge that, and see what types of reactions we can come up with. All right, in 17.1, we're looking at different mixtures. And so here they have one mixture. This is the first mixture they talk about, and that's mixing a strong acid with weak acid. Actually, before that, they have mixtures of strong acids. So if we take a strong acid like HCl and mix it with a strong acid like nitric acid, then we'll have HCl nitric. What's that going to do to the pH? Well, what you do is you take all the hydronium produced from the HCl and all the hydronium produced from the nitric and combine them. That's combined. And there's no problem with Le Chatelier's. There's no problem with this shift. Okay, now if we have a mixture of a strong acid and strong acid, then we just kind of treat it like a Chem 1A style problem. What's the total hydronium? That total hydronium is going to give us a pH. But what if we have a mixture of a strong acid with a weak acid? Well, the strong acid is going to completely ionize, completely hydrolyze, but the weak acid is only going to partially ionize or partially hydrolyze. So when we have a solution of a strong acid and a weak acid, because of the common ion effect, the weak acid hydrolyzes a lot less than what you'd expect because there's already so much hydronium present from the strong acid. And so oftentimes what we do here in a mixture of strong acid and weak acid is we ignore the weak acid because the weak acid is barely going to contribute any additional hydronium, and so the pH is dictated by the strong acid. That's the shortcut. The long way is we just do the steps. Step 1, strong acid. Step 2, weak acid. Step 3, water. But you do a bunch of those and you figure out the weak acid barely contributed anything. Was it worth doing? No, it's not worth doing unless the strong acid has very, very, very low concentration. Then you would do it. And so this is what they talk about here. They basically talk about the weak acid's not going to do much because of the common ion effect. Having a lot of product there to begin with is going to inhibit ionization. So they go through an example here of it here. So I do it in steps. They skip steps. So my step 1 would have been HCl. HCl ionizes completely. And so I would have had a step 1, and the HCl is 0.100 molar HCl, which is going to produce 0.100 molar hydronium. And so what we do from step 1 is I take that and put it into step 2. This is my step 2 here.
My step 2 is I'm starting off with 0.100 molar hydronium from the HCl. How much additional hydronium am I going to get from the acetic acid? And so I have 0.100 molar hydronium and 0.100 molar acetic acid. So I have strong acid, weak acid mixture. Okay, so let's calculate it. Well, the common ion effect is going to have huge impact here. The X is going to be a lot smaller than it normally would because we have so much hydronium here to begin with. And so when we do this, we come up and then we see this familiar thing here. So we set up the Ka, we put it in here, and then we use the simplifying assumption. And we see that X is going to equal Ka. This is common in common ion effect problem. And so it's 1.8 times 10 to the minus 5. Well, is that really going to change the pH much? And so this is going to be 0.10018. And so the change on the pH is minimal. That is, X is only 0.018%. And so the percent change is 0.018% additional hydronium, which is not that significant. So to make a long story short, we could have just skipped step 2 and step 3 and did this rapidly. Now you don't have to do that. You could do step 1, step 2, and step 3, you know, and figure it out. But if you need speed for pH calculations, then it's not, most likely it's not. Now the only time it would be required to do step 2 is if there's barely any strong acid. Let's say you had 10 to the minus 8 molar rather than 10 to the minus 1 molar HCl. Then we would worry about acetic acid because there's barely any HCl present. And so that's basically the gist of this. Now we have other types of mixtures as well. Let me make sure we're out of time. So we're going to look at other mixtures. We'll look at all of the scenarios of the mixtures in 17.1, and then we'll continue from there. Okay.